Welcome back. So, let us continue from where we left off, but before that, as usual, a quick recap of the important points that we discussed in the last lecture. We started discussing the mean variance portfolio optimization theory, and we defined certain terms and arrived at certain expressions for the portfolio possibilities curve. We started with the expected return of a portfolio with the expression that is given in equation 7 here on the slide, with for the composition vector which is given in equation 6. Composition vector means the weights attached to the various securities that form the portfolio in terms of money values, a fraction of money values of the total that is represented by the various securities that form the portfolio. The variance of the portfolio is defined by equation 8 here on the slide. There are 3 different ways in which we can express the variance of a portfolio. The first one is in the first equation, the second equation and the third equation. So, these 3 are different ways of expressing the same quantity, the variance of a portfolio of securities. Now, then we moved over to the 2 security problem. In the 2 security problem, the expressions that we saw just now a few seconds back translate to rather simple expressions in terms of the composition vector of x 1 and x 2 as the equations 9, 10 with the aggregate of the composition vectors being equal to 1, the sum of the composition vectors being sum of the compositions rather being equal to 1. So, 9 represents the expected return of a 2 security portfolio, 10 represents the variance of a 2 security portfolio, and 11 gives you the sum of the compositions of the constituents of the composition vector. If we eliminate x 2 among these equations, among this set of equations, what we get is equation number 12, and the next equation gives you the variance of the 2 security portfolio in terms of x 1. And using these 2 equations, again we can eliminate x 1 as well. So, we can eliminate both x 1 and x 2, and we get the equation of a curve in terms of as a functional relationship between the variance or standard deviation of the portfolio and the expected return of the portfolio, with the equation of that curve which represents the functional relationship between the standard deviation of the portfolio, which is captured by x here, abbreviated by x, represented by x, and the expected return which is represented by y, is given in equation number 14 here on this slide. And we saw that this equation can also be written in the standard form of a hyperbola, that is x square upon a square minus y square upon b square is equal to 1, which is equation 16, or in the form of a second degree equation as x square minus b y square plus 2 f c plus 2 f y minus c is equal to 0. I repeat, x square minus b y square plus 2 f y minus c is equal to 0, which is equation number 17, where b, f and c have the values assigned to them as shown in this particular slide. The important features of this portfolio possibilities curve, which as I mentioned is a hyperbola represented by the equation that we saw just now, equation number 14. Is first thing is that the portfolio possibilities curve must necessarily be confined to the right half plane, because sigma cannot take values, negative values, and hence there will be no point on the portfolio possibilities curve which lies to the left lies in the left half plane. All the points on the portfolio possibilities curve must necessarily lie on the right half plane, that is to the right of the origin with respect to the y axis. And if you assume that no short sales are allowed, then the portfolio return will be necessarily between the returns or the expected returns of the 2 securities constituting the portfolio, that is E of R 1 and E of R 2, which I have abbreviated as R 1 and R 2. And therefore, there would be no point on the portfolio's possibilities curve that would lie outside the region, or which is constrained by the straight lines through the points 0 comma R 1 and 0 comma R 2 parallel to the x axis. Now, then we moved over to the limiting cases of rho. The limiting cases of rho arise from the values of rho equal to +1 and rho equal to -1. We examined these two cases. Rho equal to +1 gives us the perfectly correlated securities, perfectly correlated assets, and rho equal to -1 gives us the perfectly anti-correlated assets. In the case of the perfectly correlated assets, what we have is we have the equation of the portfolio possibilities curve represented by a pair of straight lines 20 and 21. The equation 20 would operate in the region where x 1 is less than sigma b upon sigma b minus sigma a, and equation 21 would operate in the region where x 1 is greater than sigma b divided by sigma b minus sigma a. The pictorial representation of the portfolio possibilities curve in the case of rho equal to +1 is given in this slide. You can see that both the securities A and B lie on the upper straight line, that is the straight line represented by equation 20, and the region in the region between A and B, both A and B are long, both the securities A and B are long. Beyond B towards C, B continues to be long, A becomes short, and beyond A towards F and along F D in the entire region A, F, D, B is short and A is long. So, in this case the portfolio possibilities curve translates to a pair of straight lines and the intersecting the y axis at the risk free rate, which is given by r 2 sigma 1 minus r 1 sigma 2 divided by sigma 1 minus sigma 2. That is represented by the point F in this diagram. And the conclusion as far as this situation is concerned, when we have got two assets, two risky securities perfectly correlated with each other, whose prices or whose returns are perfectly correlated, then this situation or the result is that the portfolio of two perfectly correlated securities will be a pair of straight lines, will be represented on a pair of straight lines in risk return space through a common y intercept, which represents the risk free rate. The two straight lines are mirror images of each other. The upper line contains the two securities in risk return space, and the portfolio possibilities curve in this region. If no short sales are allowed, then what happens? Then the portfolio possibilities curve is constrained or is restricted to the line segment AB joining the two straight line segment line AB joining the points representing the two securities A and B in risk return space. Then we move on to the perfectly anti-correlated assets for which rho is equal to -1. Here again we have a situation where we have a pair of straight lines in the region that x 1 is less than sigma b divided by sigma a plus sigma b. The equation 26 will hold, and in the region where x 1 is greater than sigma b divided by sigma b plus sigma a, equation 27 will hold. Again you see that these are a pair of straight lines which are mirror images of each other about a line which is parallel to x axis through the point of intersection of the two lines with the y axis. Indeed, the y intercept of both these lines is the same point. So, the two lines, let us call them B f and A f, intersect the y axis at the same point which is given by the point f, which represents the risk free asset. So, this is the pictorial diagram of the case when rho is equal to -1, when the two securities are perfectly anti-correlated. The portfolio possibilities curve is represented by the pair of straight lines C f and F t, where the region B c represents the situation where A is short and B is long. The region B f A, or the portion of the two lines B f and A f or F a represents the region where both A and B are long, and then the region A d represents where A is long and B is short. The risk free rate is given by r 1 sigma 2 plus r 2 sigma 1 divided by sigma 1 and sigma 2, and this lies between r 1 and r 2. This is the interesting part. This is the important distinction between the perfectly correlated and the perfectly anti-correlated cases. In the perfect correlated case, the risk free rate was outside the interval r 1 and r 2. Here the risk free rate lies between r 1 and r 2. So, this is the pictorial representation of the case where rho is equal to -1. So, A lies on F t, that is the lower assuming that sigma the security A has a lower standard deviation than security B, lower return than security B, then A lies on F d and B lies on F c, and for the risk free rate, as I mentioned, the risk free rate is given by R 1 sigma 2 plus R 2 sigma 1 divided by sigma 1 plus sigma 2, and this lies between the returns R 1 and R 2. This risk free rate is obviously unique. So, to conclude, as far as the perfectly anti-correlated securities are concerned, any portfolio of two perfectly anti-correlated securities will be a pair of straight lines through the common y intercept. These are mirror images of each other, and the upper line contains one security and the lower line contains the other security. The portfolio possibilities curve, if short sales are not allowed, is the pair of line segments A f and F p. For general rho, when no short sales are allowed, what happens? The exact shape of the hyperbola, it is a hyperbola as we have discussed earlier. The exact shape of the hyperbola is determined by the value of rho. The closer the value of rho is to +1, the lesser would be the bulge, and the closer the value of rho to -1, the greater would be the bulge. The portfolio possibilities curve shall be confined to the section of the hyperbola that lies in the first quadrant between the lines, that is given by the equations number 26, 27 and 20. And these three equations, or the lines represented by these three equations, intersect at 3 points which are given by A, which represents one security sigma 1 R 1, the B which represents the other security sigma 2 B 2, and the risk free rate which is represented by R 1 sigma 2 plus R 2 sigma 1 divided by sigma 1 plus sigma 2. Of course, the x coordinate of f is 0 because it is the risk free point or point representing the risk free combination, and by definition we assume that the standard deviation is a measure of risk, and therefore risk freeness implies 0 value for the standard deviation. So, this is the diagram of the general portfolio possibilities curve of two securities. You can see that M is a point in between these two. We will come back to the characteristics of M, but the basic thing is that the portfolio possibilities curve, in the event that short sales are not allowed, is restricted to the arc of the hyperbola A M B, and if short sales are allowed, then of course, the portfolio possibilities curve would extend in either direction along this arc of the hyperbola beyond B as well as beyond A. So, if we extrapolate the arc of the hyperbola beyond B, that would be the region where B is long, A is short, and if you extrapolate the region extrapolate the arc of the hyperbola beyond A, then it would be the region where A is long and B is short. Then we talked about the portfolio possibilities curve with short sales allowed, which I have just discussed in the case of two risky assets. Now, we move to the agenda for today. We start with a situation where we have two securities. We have so far discussed the situation where we have two securities and both are risky securities. So, both of them have non-zero standard deviations. Now, we talk about the situation where one of the two securities, let us say the security B is a risk free security, and because it is a risk free security, by definition or by the assumption that standard deviation is a measure of risk, and because B is assumed to be risk free, therefore, sigma B must necessarily be 0. Furthermore, because the risk free asset has no correlation with any risky security, it must also be that rho would be 0 for any security A vis-a-vis the risk free security F. Let us call the risk free security F instead of B. So, let the asset be renamed F, we are risk free asset, so that sigma 2 equal to rho is equal to 0, sigma B is equal to sigma 2 is equal to rho is equal to 0, and R 2 is equal to R f. R f may not be 0, please note this point. The risk free rate of return need not necessarily be 0 at all. So, in this case the standard portfolio equations become equation number using equation number 9 and 10, we have the situation where these two equations, on eliminating composition fraction x a, we get equations number 32 and 33. Equation number 32 would hold in the region where x a is positive, and equation number 33 would hold in the region where x a is negative. Furthermore, we can see that the security A, that is the risky security that we have, lies on this the line represented by equation number 32, not on the line represented by equation number 33. Now, depending on the sign of R A minus R F, it would determine whether which of these securities is upward sloping and which of these securities is downward sloping. If R A is greater than R F, then what happens is that the equation 32 or the line represented by equation 32 would be upward sloping, and the line represented by equation 33 would be downward sloping, and the converse would be the case if R A is less than R F. So, this is a pair of straight lines which intersect each other at the y axis at the point 0 comma R F. So, this is I repeat, these are straight lines. It is quite obvious that these are straight lines, and the y intercept of both these straight lines is R F. So, both these lines intersect the y axis and among themselves at the point 0 comma R F. The security A lies on equation 32. I have already mentioned that the lines are mirror images of each other about a line parallel to the x axis through R F, because the slopes are inverse of each other. Since sigma p being standard deviation must necessarily be positive, we have the following situation. If R A minus R F is positive, and then what happens that the equation number 32 would be upward sloping, and equation number 33 would be downward sloping. And as I mentioned, security A lies on the line represented by equation 32, and therefore, we have the left hand side figure in out of this pair of figures. As far as identifying the portfolio composition along the various points or various segments represented in this figure, A F region holds, or the portfolio would lie in the region A F if both A and F are long. In other words, we have risk free lending coupled with investment in the security A. Along A C, the security A remains long, whereas we have risk free borrowing, and along F D we have risk free lending at the cost of being short in security A. So, you are short selling security A and you are investing the proceeds in the risk free asset, that is represented by the section F T extended, of course. And if R A minus R F, we have the opposite situation as depicted in the second figure or the right hand side figure on this slide. So, in the region A F, both A and F are long. Let me repeat, both A and F are long are in the region A F. Along A C extended indefinitely, A is long, F is short. F is short means you have risk free borrowing, and along F D extended, we have A is short and F is long. In other words, we are short selling A and doing risk free lending. So, this is the description of that figure. The slope of equation 32 is positive. So, that F A is upward sloping, as you saw in the diagram. In the region F A, both F and A are long. Beyond A, F is short, and the lower line represents F long and A short, as I mentioned. At F, X F is equal to 1, X A is equal to 0. Beyond F and along F T, A becomes short. If R A minus R F is less than 0, the converse will be the case as represented in the right hand side figure on the previous slide. Now, we come to the nuances of portfolio. So far, we have been addressing the foundations of portfolio optimization, or rather the shape and structure of the portfolio possibilities curve in rather simplistic situations. We now get into the nuances of this theory. We now consider the portfolio possibilities curve or the portfolio possibilities region, as you will soon find it to be, with two risky securities and a risk free security. So, let A sigma 1 R 1 B and B sigma 2 R 2 be two risky securities, and F 0 comma RF be the risk free securities. Please note, we are now considering the case where we have two risky securities and a risk free security, two risky securities and a risk free security, and A sigma 1 R 1, B sigma 2 R 2 are the two risky securities, and F 0 comma R F is the risk free security. R F is obviously the risk free rate of return. Now, this is the diagram which emanates when you can see the complexity relative to the diagrams that we have observed earlier, but I will explain each and every segment of this. This will take some time, but let us start going through it. A and B obviously represent the two securities, and F represents the risk free asset, risk free securities. Please note, we are having a situation where rho can take any values within -1 and +1, with excluding -1 and +1, because we have already discussed the cases of the two securities being perfectly correlated and perfectly anti-correlated. So, in the region FB, if you look at FB, now, let me first explain this. BC is the extension of FB, FB is the straight line joining FB, and this is being extended along C. Now, BTW is the extension of the hyperbolic arc that joins A and B. So, APB TW is the arc of the hyperbola, and as far as DA is concerned, it is the extension of the straight line FA. So, FAD is a straight line, P is an arbitrary point on AB, S is an arbitrary point on FP extended, and Q is an arbitrary point which lies between P and F. So, this is the description of the various symbols that we have on this slide. Now, let us see what each of these lines and the symbols represent. So, as far as FB is concerned, it is quite obvious that it has to be a linear combination of securities F and B, with both securities being long. X F and XB will both be between 0 and 1 in the region FB. Now, what about BTW? Along BTW is the extension of AB along the arc of the hyperbola APB. This continues onwards to TW. Therefore, because T and W lie on this arc of the hyperbola, they will be combinations of A and B only. In fact, beyond B, if you go along BTW, then B becomes long, or B continues to be long, but A starts becoming short. At the point B, XB is equal to 1, XA is equal to 0, and there is of course no XF. But as you move along BTW, along the hyperbolic arc, I reiterate, then XA starts becoming short, XB continues to be long with being greater than 1, XB being greater than 1, but XF continues to be 0, because there is no involvement of F insofar as this hyperbolic arc is concerned. In other words, I will come back to it, except for the point T, there would be no point on this arc A, B, and even at the point T, of course, there will be no point here where X F would be having a positive or negative value other than 0 along the arc of the hyperbola A, B, T, W. So, BTW represents B long and A short. BC, now BC is what? BC is the extension of the straight line joining FP. So, at the point F, we have XF equal to 1, XB equal to 0. At the point B, we have XB equal to 1, XF equal to 0. And if you move along the same straight line to along BC, then XB becomes greater than 1 and XF becomes less than 0, which means that we are having risk free borrowing. So, what you are doing is, along BC you are borrowing risk free and you are investing in the security B. Then at the point T, what is the point T? First let me explain. The point T is the point at which the tangent is drawn from the point F. Tangent is drawn from the point F to the hyperbolic arc AB extended if required. I repeat, T is the point at which we draw a tangent from the point F to the hyperbolic arc AB extended. So, at the point T, Ft is tangent to the arc ABTW. So, at the point T we have A long, because it lies on the hyperbola AB. So, we have A long, we have B I am sorry, we have A short, we have B long, and we have no involvement of risk-free lending or borrowing. But beyond T, if you go along the straight line Ft beyond T, then short risk-free borrowing starts, and then you have risk-free borrowing together with the long position in B and the short position in A. So, you have short positions in F and short position in A and a long position in B if you move along Ft straight line extended, where Ft is the tangent, I repeat, Ft is the tangent to the hyperbolic arc AB extended. So, Ft, F and B long, along the line Ft, of course, what will you have? You will have, you see, now please note this interesting point. Along the line Ft, what will you have? You will have the linear combination of F and T. At the point F, xf is 1, xt is equal to 0, at the point T, xf is 0, xt is equal to 1. But what is xt? Xt is xt lies on the arc of the hyperbola AB. Therefore, it must be a combination of A and B with, because it is extended beyond B. That means, xb and xa would be in such a proportion that xb is long and xa is short. So, along Ft up to T, F and B are long and A is short. And what about AB? I have already discussed. AB is the arc of the hyperbola, and at any point along the hyperbolic arc, we shall have A and B together, either A long, B long, or one of them long and one of them short. But within A and B, along the arc AB, within A and B, there would be no short cells, and both A and B would be long. If you extend beyond B along the arc, then B becomes long, A becomes short. If you go beyond A along the arc, then A becomes long, B becomes short. So, what about FA? FA is the straight line where it is a linear combination of A and F. So, obviously, in the segment FA, A is long, F is also long. In other words, you have a combination of risk free lending and investment in security A. But if you move beyond A along AD, then what happens? Then A becomes continues to be long, but F becomes short. In other words, you have risk free borrowing and the investment of the borrowed proceeds in security A. AD I have discussed. What about the point P? Now, this is interesting. Point P is an arbitrary point between A and B along the arc A and B. I repeat, point P is an arbitrary point along AB within A and B, that is along the arc AB, and it lies somewhere within A and B. So, it must be a combination of securities A and B with both securities being long. Now, what about FP? FP is a straight line which is bounded by F and P. So, it has to be a linear combination of the portfolios represented by F and P. That means, at the point F, obviously, we have xf equal to 1, xp equal to 0. At the point P, we have xp equal to 1, xf equal to 0. And if you take any arbitrary point Q in between F and P, then it would be a linear combination of F and P, but P itself is a combination of securities A and B both long. Therefore, at any point Q which lies between F and P, both or all the three securities F, A and B would be long. And please note, this is any arbitrary point within the region B, F, A, bounded by the line segments B, F, bounded by the line segment A F, and bounded by the arc A B. So, if you take any point bounded by these 3 points A, F, FB and the arc AB, then you have a combination where all the three securities would be long. So, this region of space lying between FA, FB and the arc AB will represent combinations where all the three securities are long. Now, what about the point S? S is a point outside the arc towards the right of the arc AB. Now, obviously, at point P we have x p equal to 1, x f equal to 0, but if you move along f p beyond P, then what happens is that x f becomes negative, x p becomes greater than 1. So, the point S represents the risk free borrowing and the investment of the proceeds in the combination represented by the point P. So, at the point P what do we have? I am sorry, at the point S what do we have? We have short in F and long in the securities A and B. So, I have discussed almost all these regions and all these positions of various points on this diagram. It is very interesting and it will help us in understanding what is to follow from here on. Now, we can have different scenarios as I explained in the diagram previously. We have different situations where one security can be long, the other can be short, or two can be long and the third can be short, or all three can be long. So, on that basis I have classified the portfolio composition into different scenarios. We have 6 scenarios here. First of all, we have a situation where no short sales are allowed in A and B and there is no risk free lending or borrowing. Then we have short sales in A and B, but no risk free lending and borrowing. Then we have no short sales in A and B, but we do have risk free lending. Then we have no short sales in A and B, but we do have risk free lending and borrowing. Then short sales with risk free lending, but no borrowing, and then finally, the most general situation where we have short sales allowed as well as risk free lending and borrowing allowed. So, let us take the first case now. In the first case, we have no short sales allowed, no risk free asset. As I mentioned earlier, in this case the portfolio possibilities curve we have discussed it in a lot of detail. It will be the arc of the hyperbola confined between the points A and B. So, I repeat, in the situation where there are no short sales in A and B and no risk free asset is there, that means there is no risk free lending, there is no risk free borrowing. In that situation, the point representing the portfolio will lie on the arc A and B, for example, the point P. P is a typical point where we have combination of A and B both long with no involvement of the risk free asset F. So, in the case of no short sales with no risk free asset lending or borrowing, either case the portfolio possibilities curve is the arc of the hyperbola lying between the two securities A and B. Then we move to case 2. In case 2, what do we have? Short sales in A and B are allowed, but again we do not have a risk free lending, that means no risk free lending, no risk free borrowing, but we do have short sales in A and B allowed. In this case, what happens is the portfolio possibilities curve gets extended along the arc of the hyperbola beyond A and beyond B as well. So, in other words, the entire arc of the hyperbola AB extended in both sides, extended beyond A along the arc of the hyperbola and extended beyond A as well along the arc of the hyperbola will form the portfolio possibilities curve. If you take a point beyond B on the arc of the hyperbola AB, it will represent B long and A short, and if you take any point beyond A along the arc of the hyperbola, you will find it to be A long and B short, and of course, along AB along the arc in the region AB both A and B would be long. Now, we take the next situation where no short sales in A and B are allowed, but risk free lending is allowed. In this case, what happens is I have explained briefly this situation. The portfolio possibilities region, this is not a curve, it is a region of space. The region of space is the space which is bounded by the straight lines or line segments BF or FP, FA and the arc of the hyperbola AB. So, this region which is bounded by these three to this pair of straight lines and the arc AB constitutes the feasible region, constitutes the portfolio possibilities region in a situation where neither any short sales are allowed nor risk free borrowing is allowed, but risk free lending is allowed. For example, if you take any arbitrary point q here, q is a linear combination of f and p itself is a combination of a and b, both being long. Please note, because p lies between a and b, therefore p is a combination of both a and b, both being long. Because q lies in between f and p, both f and p are long in q and p is long in a and b. So, the net result is that for q being any arbitrary point between b, f, a, the three securities, all the three securities would be long. We shall continue from here after the break. Thank you.